Hello viewers, welcome back to the channel. Today we will be doing a very important problem from the textbook Mechanics of Materials written by Timoshenko and Gere. See, this particular question is very important as it opens up to a whole bunch of concepts. And believe me, a similar kind of question was asked to me, in fact, when I attended the interview for Exxonmobil. Exxonmobil is a huge oil company. So this similar kind of problem was asked when I attended the interview in their campus. So let's begin. Here we have a two bar assembly. The first segment is made of steel and the second segment is made of aluminium. It is rigidly fixed at these 2 points, and if you read the problem very carefully, I will show you the whole question in a while. So I request you to pause this video and read through the question very carefully, as I always say, because reading the question with full amount of concentration will ensure that you getting the answer right, you getting to know what the other person is actually looking at. So a very important piece of information is here. It is this thing which is, you can see in the middle, it is rigid. The aluminium and steel pipe shown in the figure are fastened to rigid supports at end A and B and to a rigid plate at C. So what do you mean by a rigid body? Rigid body won't have relative displacement. You take any 2 points in the body, there won't be any relative deformation. Makes sense? So we don't have to consider the Young's modulus and all those properties of this fellow, this rigid plate which is seen over here. Makes sense? Now let's move ahead and see how we can solve this problem. If you look at carefully, this is a statically indeterminate problem. Okay, there are a lot of ways in which you can do statically indeterminate problems, but the one which I'm going to pick is relatively simple. You don't have to learn these methods by their names, you just understand the concept. See, what I'm going to do now is I'm going to remove this particular support from here and I'm going to replace that with a force or with a reaction at that point. So the problem I'm going to solve now will look something like this. I'm going to remove that support. I'm in this figure, in fact, I've removed both the supports, but the problem which I'm going to solve will be something like this. I'm keeping the support on the top, but I'm removing the support at the bottom. It's not done. When I'm removing the support from the bottom, I need to replace it with an equivalent reaction force. Let me call that RB, capital RB. Okay, and I will call these points, this is capital A, this is capital B, and this is capital C. Make sense? Now this becomes a statically determinate problem. Make sense? But some things we need to ensure as we solve this problem ahead. When we solve this problem ahead, the tactics is very simple. Let me explain the tactics first, then we will go ahead and solve the problem. The tactics goes like this. Now you will consider the equilibrium of each of these segments. Whenever we do simple solid mechanics problems, there are three things which we need to worry about. One is the equilibrium. Second is the compatibility. I will come to that in a while. And the third thing you need to bother about is the constitutive law. Constitutive law. Make sense? So these are the three rules which you need to keep in mind while solving every particular problem. So in solving this problem, I can take into the considerations of equilibrium and then find out what is the resultant force acting in each of these members. Then there comes the second fellow, compatibility. If you look at closely, in the actual problem, this point C is rigidly fixed. So when we solve this problem, we will get some amount of displacement for the point C, isn't it? It will be non-zero. But in actual problem, displacement of C will be 0. So once we impose that constraint into the problem, then we will be able to solve the problem completely. And in order to get the strains or whatever quantities you are looking at, you can use constitutive relations. Make sense? That is the strategy that we are going to follow for solving this particular problem. Let's get started. See, the first thing that I'm going to do is compute the relative displacement of this particular point C with respect to B. So it is as good as imagining that this point B is rigidly fixed and we have a force acting at the point C acting in this direction. Okay, makes sense? So now this one reduces to something like this. You have a bar which is fixed at the point B. Then we are applying a force like this. This is a relatively simple problem to solve it, but have a keen look at the way how I have named it. I'm naming it as delta C B. What is that? The displacement of the point C with respect to B. That's why I can use this expression where RB is the force and 2L is the length of this bar. Make sense? So the key concept or the key takeaway is that this is the displacement of point C with respect to this point B. Clear? I have an expression in terms of all the non-quantities. Make sense? Now we can similarly compute what is the displacement of the point B. Point B is somewhere here. What is the displacement of this point with respect to A? A is fixed, so that is 0. But even then, what is the displacement of the point B with respect to A? That can be also computed. One more thing I need to drive home is that the net force acting at this section is RB. Because if I take a small chunk of material from here and then draw the free body diagram, it may look something like this. I have a net force RB acting like this from this portion. Then I will have some resultant distributions, the stress distribution or whatever, some distribution in this on this face whose resultant will be again RB. For this particular portion to be in equilibrium, this is the net force acting in that section. That's why we saw an RB in this expression. So now using a similar logic, when we compute what is the deflection of the point B with respect to point A, we need to account for the net force acting at this section, somewhat at this location. What will be that force? Again, in order to compute that force, we need to draw the free body diagram. Free body diagram is a very handy tool. I've been telling this throughout my videos. So if you have a good hand in drawing free body diagrams, then half of your problems are solved. So we have a force 2P acting at the middle. So I'm cutting a section somewhere here. Please bear with my poor drawings. Then I have a force RB. If I take my positive direction of forces in this direction, let's say this is my positive direction of the forces, then the force acting at this section will be RB minus 2P. Why? Because if this force is RB minus 2B, then if you add up all the forces in the y direction, then you will get 0, which is a necessary condition, isn't it? This thing is not accelerating, this is not moving, this is at static equilibrium. So it is at static equilibrium. So then if you sum up the forces acting along the y direction, you should get 0. Make sense? So that's why instead of RB, when you are computing the relative displacement of point B, you can see RB minus 2P over here. Make sense? Now, common sense question. common sense question. What will be the displacement? What will be the total displacement of point C? The total displacement of point C will be the delta CB, which gives you how much point C has moved with respect to point B, plus how much point B has moved with respect to A. A is at 0, so if you add these two quantities, then you will get what is the net displacement at point C. Make sense? So once you do that math, you will reach somewhere here. Make sense? But now we bring in the constraint which corresponds to the real scenario. In the real scenario, the point C is totally constrained. It is not allowed to move. So that means once you add these two quantities, you should get 0. Now, rest of the things are just turning the mathematical wheel or cranking the mathematical wheel. Using this particular expression, we can have a formula for RB. RB is the reaction at the point B. It is acting in this direction, the upward direction. We assumed RB is acting in the upward direction. So if you get a positive value for RB, then that means your bottom member will be this one. Your bottom member will be in compression because your RB is positive. So this thing will be this particular bar will be under a state of compression. Now if they ask you to compute what are the stresses in the aluminum bar, then it is simple because the force divided by area will give you the stress in the corresponding bar. So if you want to compute the stresses in aluminum, it will be simply a the reaction RB divided by area of aluminum, and the stress in the steel will be RB minus 2P divided by area of the steel, because this is the force acting in the steel segment. So what you learned in this problem is how to solve statically indeterminate problems, and always use the concept of free body diagrams when you are asked to find the force acting in each of these sections. Then when you are doing a statically indeterminate problem, it is not different to a normal problem, but you need to just keep in mind that the constraints that comes as part of the statically indeterminate problem, like how we solved for the displacement at this point, and finally then we enforced the displacement at this point to be 0. So no new techniques. Solving statically indeterminate problems are not difficult. It is just common sense. That's it. Thanks for watching.